Good day, friends. My name is Marat Gazizov. I'm senior lead of the team that develops tools for document recognition in the bank. My companion is Stepan Evstifeev. He's a CV engineer of SberOCR 360 that develops some models for our solutions. The topic is recognize everything about SberOCR, but I would call it another way: how to put 33 models together and not go crazy. So, let me tell what's this all about. Sberbank is an enterprise and many processes are based on the documents. There are processes intertwined with the document routing, checking document completeness, extracting entities from documents. To do this, you need large platform. We have it, and it's called Intelligent Document Processing. At this moment, it processes about 1.3 million documents per day. What kind of documents are these? Usually we need to recognize scanned documents, but we also work with handwritten documents, documents with tables, ID documents, passports, SNILS, INN, and so on. Apart from documents, the text can be present on other surface. We separate in the wild entities, which are images with text, for example, images taken with a smartphone. So, why are we talking about this? Even 5 years ago, if you ask how to recognize documents, your obvious option would be using proprietary software. However, in the past few years, we found out that deep learning didn't only change NLP and CV, but it also changed document recognition. Many teams on the bank make their own state-of-the-art models to recognize documents, to digitize documents, and we decided to find out the reason. Turned out, it's quite simple. Open source provides state-of-the-art models with the ability to fine-tune them for you, specific document type, which is an advantage. So we decided to define is we can combine advantages of two worlds, open source solutions and proprietary software. In particular, we called this solution SberOCR. It's a framework that allows you to create and use state-of-the-art models and reproduce results, fine-tune models for your document types, and prepare them for production environment. Usually, when people talk about document recognition, they mean two types of models: text detection and text OCR. In fact, to ensure quality recognition and make sure you can use it further and give the result as an input for other models, you'll need more than that. For example, if the document comes in corrupted, you need to restore projected distortion. There's a separate rectification model for regeneration of the corruption. Then there is text detection. But to analyze document structure correctly, apart from text, you'll also need to find structural elements, such as stamps, signatures, logos, and tables. You also would want to parse tables. After this, we need to tell, what is this text? What is its language, and if this is printed or handwritten? Only after that there is OCR. It's already quite a lot of modules, but that's not it. In the end, you need to gather output material in some reading order to keep the narrative logic. There are also separate modules to ensure that. So, if you do all this work, which we did, you get this beautiful result. On the left there is a document. Green highlights are words connected into lines connected into paragraphs. There are stamps, signatures, and tables. On the right, you can also see the result of tables parsing. Apart from that, we can work with handwritten text and we can recognize it. SberOCR is quite a large solution. Several teams work on it right now. In the upper part, you can see modules inside the product. There are about 10. In the bottom, you see production pipelines. These are modules that allows you to create SOTA models and fine-tune them to fit your document types. Right now, there are 33 models in our garage. Half of them are OCR models, various language models, and half of the models is distributed between modules. In fact, it's quite a lot, and you need to know how to manage them. Apart from our solution, I would like to tell how we ensure inference, share interesting observations we found when trying to make this as efficient as possible. What are the requirements and characteristics of the inference pipeline? We highlighted several points: unification, optimization, verification, and result repeatability. We can talk about verification and result repeatability, but the time is restricted, alas. Within this presentation, we'll talk about the first two components, unification and optimization. Unification is simple. At some point, you understand that you need an ability to divide training pipelines, dependencies in training pipelines and production environment. How to do it? We chose the simpler solution. We abstracted the training pipeline layer and separated a registry module that stores completed modules. What are the completed modules? They are two files, nominally two files, let's call it two objects, emo-config that describes all the pre-processing steps, post-processing steps, and model features. Here on the right, you can see an example of this config and the binary model itself. For example, we work with JIT, ONNX, OpenVINO, TensorRT. Next, when your production pipeline created the models, you store them in registry module. I'll explain why this is needed. Now, let's talk about optimization. Optimization is interesting. Our product environment is a cluster with dynamic infrastructure where we can deploy many stateless Docker containers. So we don't have issue with data-level parallelism. If you have a document consisting of tens and hundreds of pages, we can process it quickly by dividing it into parts and launching parallel computation on the cluster. But our task is different. We need to have the ability to process each document page as quickly as possible. In particular, each container has 4 to 8 vCPUs that can be considered cores. The image resolution 2K like in a good TV. We work a lot on optimization of our solutions, but I would like to talk about two components: model quantization and choosing model engine. Originally, I was talking about unification. We know how to ensure unification on the model level, but we would like to ensure unification on the engine level. Let's consider our options. In fact, the market is a lot of frameworks, open source frameworks, which you can use for model inference. What we consider an engine. In essence, that's how your convolution is written and the way the operation of array multiplication is written on the lower level. Performance of your models depends on how efficiently it's implemented. Returning to unification, we would like to choose an efficient engine. We've made a series of research in order to find this very engine. Let me describe the content of the big table on the slide. We chose two types of modules, CNN and RNN. I'm not specifying architectures on purpose because we found out that even changes of specific layer types can greatly affect the final results. So naturally, you will have to reproduce these results for your architectures. Also, we perform experiments with two types of accuracy, model accuracy. These are FP32 and INT8, our quantized models. Without much detail, you can say that INT8 is generally faster and is calculated faster than FP32. Here's an example. Imagine you are asked to find a sum of 2 pi. If you calculate an integers, you will say 6 right away. If you need to calculate with some degree of accuracy, it'll take a bit more time. The situation here is similar. Manufacturers also add optimization on the hardware level. Let's look closely at the table. We found out that if you choose CNN with FP32 accuracy, the optimal engine for this configuration is ONNX runtime. If you get to quantized models and your models are in INT8, then it's interesting to know that the leader is OpenVINO. At the same time, ONNX runtime works even slower than FP32. I added the link below where you can see that this framework actually has problems with optimization for INT8. When we get to other architectures, for example RNN, it turns out that the landscape changes again. And here the PyTorch jet of the multiprocessing starts to shine. Turned out that OpenVINO has quite big latency for reshape operation for operations with sequences of different length. Inference is the most efficient when we use PyTorch jet, which doesn't have these problems, and add multiprocessing on the data level. It seems crazy, because we wanted to find the best framework, but it turns out there are 3 frameworks for different types of models, and when there are a lot of models, one of them will most likely be in this or that state. So, you most likely want to have an opportunity to switch between the engine frameworks. Here on the slide you can see another level of abstraction called engine registry. These are sets of frameworks supported by SberOCR. In particular, we can switch between and configure for each model and module its own framework. So, we can even use several frameworks during inference in one pipeline. What are the advantages? Well, the first advantage is interesting. This is weird, but you can deny all framework except for one. For example, if you deploy on GPU, then your option is TensorRT. If you deploy on CPU, you might choose ONNX runtime, and you won't have to drag all dependencies from train pipeline and other engines. The second advantage is that if you need the maximum performance, you can choose. You can run one module on one engine and another module on another engine. The third advantage is that there is such thing as parallel runner. This module allows to launch other modules in parallel on different devices or even on the same device, but in several processes in threads. This allows you to utilize GPU and CPU resources within the same pipeline, while still using different engines for optimum operation. We worked on our baseline. The first line here is our baseline. We've done what I talked about on our baseline, and it shows 4.7 seconds. It's a 2.8 times growth. Now our solution worked for about 1.65 seconds. Because of quantization, we got a little decrease in accuracy, but as you can see, it's quite small. We also compared our solution with other open-source solutions. The closest would be probably the production Tesseract. Tesseract needs 3 seconds per image. Also, just about a month ago, there was a release from Paddle. Their solution without layout shows 2.3 seconds. Here I'd like to say that apart from framework development and engineering tasks, we also conduct a lot of research. In fact, one of the main tasks is to provide our customers with the state-of-the-art models. Now I give the stage to Stepan, who will talk about our research in table recognition. Stepan? Thank you, Marat. Hello, everybody. My name is Stepan. I work in Sber, DK360, and today I'll talk about table recognition. In enterprises, a lot of information is presented as scanned documents. These documents need to be digitized for further processing, and in case of simple documents that only contain text, you only need to find and recognize words. There are such tools in SberOCR, but there's also a separate layer of documents where information is presented as tables. For example, invoices, financial statements, etc. That task is different because apart from the word content, there is also its position in the table. Moreover, empty cells without text also imply information. The task is even more complex because some people have to clear lines, which make reconstruction difficult. There are also cells groups or spans. For example, on the figure to the left is the original table, with no clear lines, and each block headline is a span. On the right, you can see it recognized table where cells are marked green, and bold lines are spans. Let's review existing solutions and why they are no good for us. There are 3 large algorithm groups, and they are all based on the deep neural networks. The first approach uses SOTA models for object detection to predict cells' boundaries. Its disadvantage is that it doesn't take task specifics into account, but we work with tables that have some structure. The second approach is segmentation approach. It divides the task into 2 parts, split and merge. I'll talk about them later. The main disadvantage is that 2 separate models are used for these tasks. The third approach predicts coordinates of words and HTML structure of the table. This approach is SOTA, so we'll look at it at more detail. This SOTA approach, so-called EDD model, consists of 2 parts. Encoder is a convolutional network that extracts images, features, and decoder, which is GRNN that predicts HTML structure and content inside cells. There are 2 obvious disadvantages of this architecture. The first is shown on the left. Predictions of this model are inconsistent, and one word may have several predictions. The second problem is shown on the right. The coordinates of words in this model are quite inaccurate because of the regression part of the network. So, We were looking for other approaches and chose segmentation approach that doesn't have disadvantages above. We also split the task in two parts. Split part is finding all possible cells on the image, and merge part is merging the cells into spans. Below is the result of each stage. Although we were inspired by segmentation approach, we made a series of significant additions and found a solution for main problems of this approach. First of all, we use SOTA solutions for segmentation instead of architecture. Instead of two models, we use one resulting into end-to-end solution. Instead of heuristic in the merge part, we predict connections between cells right away. Below is the high-level architecture of the network. The table is an input for segmentation network. The output of segmentation network is sent to three separate heads, which we'll review later. Their outputs are assembled in post-processing, resulting in recognized table. The heads are small subnetworks. There are three of them. The first head is responsible for predicting connections between cells, and the other two are responsible for projecting separators between cells in horizontal and vertical lines. On the slide, you can see algorithm output compared to other solutions. The map metric is a classic metric from object detection for cells coordinates, and the TEDS metric is a special structural metric for tables that calculates start. So, how many operations are needed to translate the predicted HTML into the correct HTML? The closest analog of this metric is the Levenshtein distance. As you can see from the table, our solution provides better predictions of cell coordinates, and in the structural metric, we are on par with the current SOTA solution. But the TEDS metric has one aspect. Unlike map, it doesn't take resulting cell coordinates into account. So there can be a situation shown on the left. This is a prediction of EDD model where the model structure is predicted correctly, but the word cells coordinates are predicted inaccurately. On the right, you can see the output of our model. The structure and cells are recognized correctly. So, we cannot rely on the metric in this task. That is for me. I give the word to Marat. Yes, Stepan. Thank you very much. I would like to say a couple of words. As I said, apart from framework development, we also do a lot of research. On the slide that you can see, the topics we work on right now or plan to work in the closest future. In particular, we are interested in models. Fusion models are multitask models, end-to-end solution, solution for synthetic data generation for handwritten texts. In the right bottom part is the output of our models. Our colleagues in the workshop section talk about our solutions in this area, so you can listen to them as well. I would also like to add, if you're interested in one of these topics, and you would like to work on it and get it to production, send us a message or call. We would love to discuss this. We're looking for CV engineers and researchers as well as ML engineers. If you didn't see your position here, send a message as well. I'll think we'll find a solution for sure. That's it. Thank you very much. The presentation is over.